Welcome to our favorite YouTube channel DCD Electrical Knowledge. Today's goal is to learn stepper motors, precision in every step, specialized electric motors converting electrical pulses into discrete fixed angle movements, ideal for high precision applications, that is robotics and automation, unlike continuous rotation motors. Stepper motor and standard DC motor. A stepper motor is a brushless DC electric motor that divides a full rotation into a number of equal and discrete steps. It is also known as step motor or stepping motor, since the special type motor rotates in steps, so it is called stepper motor. Moreover, stepper motor is constant speed type synchronous motor. The question is that why stepper motor is called synchronous motor? We know that in synchronous motor, AC supply is given to the stator and DC supply is given to the rotor. That is, in synchronous motor, AC supply and DC supply both are required. In stepper motor, AC provide pulsating magnetic field, that is positive and negative pulse at the stator through microcontroller and motor driver chip, that is the brain. The DC provide fixed pole, that is permanent magnet at rotor. This is functionally and constructionally resemble as synchronous motor. That is why stepper motor is called synchronous motor. Unlike standard DC motor that spin continuous when voltage is applied, stepper motor rotate a specific number of degrees based on digital control pulses. Apply power, it spin continuously, that is standard DC motor. Whereas in stepper motor, it moves in exact discrete step, perfect for precision. Defining the step. One revolution of a rotor covers 360-degree mechanical. That is, step angle is equal to degree per step. Step angle is equal to how much angle moves in on step. Mathematically, step angle is equal to 360-degree by number of steps. It decides the accuracy of the motor. If the step angle decreases, number of steps increases and accuracy of the motor also increases. Maximum step angle should be 90-degree and minimum step angle is equal to 0.72-degree. A standard motor has 200 steps per revolution. A specification of stepper motor is NEMA 17. So, step angle is equal to 360-degree by 200, that is 1.8-degree per step. Generally, step angle of stepper motor should be 1.8. Otherwise, it may be 2.5, 7.2 or 18-degree. Higher step count is equal to finer resolution is equal to smoother, more precious movement. Anatomy of a stator motor. Precision in every step. How does it know exact where to stop? Why so many wires is there? Construction of stepper motor. Stepper motor has two parts like other motors, that is stator and rotor. Stator, the stationary part, the outer ring of wire coil, these are the electromagnets. They do the pulling work. As and when required, stator is used as multipole and multiphase. Sometimes this phase is known as stake. A rotor, the rotating part. Rotor of the stepper motor is a permanent magnet. That is, polarity is constant, having no winding, no brush, and no commutator, having only variable reluctance teeth. These teeth is sometimes resemble edge pole. The central shaft that spin it gets pulled by the magnetic field. Beware and danger. Never manually force a stepper motor to spin quickly by hand. The stator coil will act as a generator and fry your drive board. Stator versus rotor. The stator, the electromagnet, coils, copper wire warped around iron pole. When current flows, the poles become an electromagnet. The rotor, the magnetized core, sits perfectly inside the rotor. Also features tiny teeth around its outer edge. Electromagnetic stator plus tooth rotor is equal to magnetic attraction. The principle of reluctance. The magnetic flux seeks the path of least resistance. The motor works by creating a magnetic void and forcing the iron rotor to physically shift to close to the gap and align with the magnetic circuit. The air gap is equal to high reluctance. Figure shows the rotor and the attractive force and electromagnet. The physiology, how it moves. There are two sets of teeth. The upper set is the stator's teeth, and the lower set is the rotor's teeth. Rotor teeth physically rotate to align perfectly with the magnetized stator teeth. Nature loves balance. It finds the path of minimum magnetic reluctance. The working principle step by step. That is how it actually steps one page on. As per figures, step 1, page A energized. Step 2, page B energized. Step 3, page C energized. Step 4, page D energized. By energizing the stator coils in a specific sequence, the magnetic field rotates. The rotor simply chases the rotating magnetic field around in a circle. Thus, we drag the rotor around with it. The secret: intentional misalignment. Stator phase A and stator phase B, separately shown in figure. Look closely. When phase A is aligned, phase B is slightly misaligned on purpose. If they all lined up at once, the motor would not know which way to step next. The misalignment creates the physical pull for the next step. The stepper species. Stepper motors can be broadly classified in three types on the basis of the construction of rotor. 1. Variable reluctance. 2. Permanent magnet. And lastly, hybrid, the child of VR and PM. Different jobs require different rotor designs. Let's look at the three main types step by step separately. Species 1: Variable reluctance VR. Rotor is just a solid block of soft iron. Has teeth, zero permanent magnet inside. Operates purely on the principle that iron wants to align with a magnetic field. For minimizing reluctance. Pros: fast and simple. Cons: lower torque, twisting force. This type of motor consists of a soft iron multi-tooth rotor and a wound stator. When the stator winding are energized with a DC current, the pole becomes magnetized. Rotation occurs when the rotor tooth are attracts to the energized stator poles. Species 2: Permanent magnet, that is PM. A rotor is a permanent magnet, no teeth, completely smooth, uses the basic push or pull of magnets. Stator electromagnets attracts the opposite pole of the rotor magnet. Pros: good torque. Cons: low revolution, that is few step per revolution because it has no tiny teeth. It is also known as tin can or can stock motor. It is low revolution type motor with typical step angle of 7.50 degree to 1.50 degree, that is 48 to 24 steps per revolutions. Species 3: Hybrid stepper motor. Has a permanent magnet core like PM. Magnet is capped with tooth iron like VR. The industry standard combining the torque of a magnet with the precision of iron teeth. Typical step angle 3.60 degree to 0.90 degree, that is 100 to 400 steps per revolution. The hybrid stepper motor combines the best features of PM and VR type of stepper motor. The species comparison: rotor material for VR iron, for PM magnet and hybrid magnet plus iron. Has teeth. VR has teeth also. Yes. PM no, and hybrid yes. Step resolution: for VR medium, for PM low, and for hybrid motor is very high. Torque strength: for VR low, permanent magnet, that is PM, is high, and hybrid motor very high. Best of the both worlds used in almost all 3D printers and robots today. Control methods: the brain. The motor is just dumb hardware. It needs a driver to tell it which coils to turn on and when. Microcontroller sends step and direction signals. Motor driver chip sends heavy electrical current to motor coils. By changing how we turn the coils on, we can change how the motor behaves. Drive method 1: wave drive. The most basic control sequence. Only one phase is activated at a time. The rotor moves directly from one stator pole to the next. The graphical representation shows that phase A, 1A coil, phase B, second step B coil 1, and phase C, third step C coil 1, and fourth step D coil 1. Characteristic: simple logic, low power consumption, and low torque output. Drive method 2: full step drive. Two phases are energized simultaneously. The rotor aligns itself exactly in the middle between the two active magnetic poles, resulting in significantly higher torque. Figure shows the voltage level versus time graph. Step 1, phase A1. Step 2, phase A and B on. Step 3, phase B and C on. And subsequently, phase C and D on for fourth step. Characteristics: maximum holding torque, standard industrial operation mode. Drive method 3: half stepping. By alternating between activating one coil, then two coils, the driver forces the rotor to stop exactly halfway between full step, doubling the mechanical resolutions. Figure shows the voltage level versus time graph. Step 1, coil A on. Step 2, A and B on. Step 3, B1. Step 4, B and C on. Result: 200 physical steps digitally transformed into 400 step. Full stepping versus half stepping. Full stepping, coil A on, coil B off. Turn on coil at a time, rotor aligns with that coil. Half stepping, coil A on, coil B on. Turn on two adjacent coils, a rotor balances preciously between them. Half stepping literally doubles the physical resolutions of the motor without changing any hardware. Pulling it all together, system architecture. The brain, the muscle, the joint, as per the diagram. The brain sends tiny logic signals up to 5 volt, take 100 steps clockwise. The muscles takes the tiny signal and acts as a higher power switch, routes a heavy current from the power supply. The joint coils magnetized, rotor aligns, physically executing the previous step. The ticking heart of automation. While DC motors spin widely, the stepper motor counts its space, making modern robotics, 3D printing, and automation possible. It is predictable, precious, and powerful. No more today. Next, we meet you in next forthcoming videos. Please like, share, and subscribe my channel DCD Electrical Knowledge. Thank you.